Okay, welcome back everyone. IMR CDT, Lecture 7, Theory and Simulation. We'll continue today with looking at the mathematical foundations of spin dynamics. We explored in the previous lecture spaces and Hilbert spaces. We saw how they arise out of sets and fields once you equip them with addition, operation, multiplication by a scalar. We looked at linear combinations, basis sets. We introduced scalar products and norms and made them into Hilbert spaces. And today we'll just continue up this diagram and introduce the other necessary things that often appear in spin dynamics, namely algebras, Lie algebras, and two different kinds of groups, the discrete and the continuous groups, which are called Lie groups. Now, if you remember in the previous lecture, what we did is viewed the members of this set as something abstract. They could have been vectors, they could have been matrices, they could have been something else. Today I would focus specifically on operators. Now this doesn't reduce the generality in any way because it would apply just as well to any other things in here. It's just we need to get a bit closer from the pure maths into the context that we've got in quantum dynamics simulations. We can of course make it really, really rigorous, but it would, as a result, be really, really useless. It has to have some relation to physics. And as we'll see later today, the definitions concerning the algebras is where the mathematical tradition does actually come into conflict with the physical tradition, and we will take the physics side in the way we define the Lie bracket. Okay, now we've got those operators. We made their linear combinations. What we didn't have at the end of the previous lecture was operator products. And what I'll do now is, before I start going into formal definitions, I'll just quickly run through and mark down perhaps the simpler contexts in which these things appear in our simulations. Right, so if we take a set and we simply allow pairwise products, and importantly inverses, what we get is something called a discrete group. And examples of this kind are finite groups that we have in molecular symmetry treatment, crystallographic point groups of crystal lattice translation and rotation, then permutation groups of the finite number of objects and such like. What's important is the set must be closed under the product and there should be a unique inverse. As you notice here, there's no multiplication by a scalar and there is no addition. So group in that sense is something that's quite different from spaces. Now, if we go from here and require the preservation of these two operations, which are really useful in quantum mechanics when we work with density matrices or wave functions, and instead allow the product in there, what we get is an algebra. And algebra contains multiplication by a scalar, it inherits it from the space, it contains addition, but it also contains the products of operators. But it needn't necessarily, unlike the group, be closed under the inverse. So the operators in here might, and often are, in fact non-invertible. And if we look at what algebras are, most operators that we have in quantum mechanics, they live inside algebras. So there are operator algebras. In particular, a Hamiltonian is a sum with some coefficients of some products of some operators. So it clearly belongs to the algebra. Now, with spin operators, we additionally will introduce the commutator, and in addition to all of this infrastructure, we'll also be taking commutators. And once we build our spin Hamiltonian, its exponentiation will take us into a group which would contain infinitely many elements. For example, there are infinitely many time propagators under a given Hamiltonian. But because this is an exponentiation process here, if a group contains an element, it also contains its inverse, which just flips a sign under the exponential. And so it's similar in a way to this, except in this case it's not a differentiable manifold. They occur separately, whereas in the case of Lie groups, it will be a differential manifold. It will be continuously parameterized by some parameters. And so things that live here are rotations, for example, in the sense of continuous rotations of a sphere, and time propagators, as I noted already. So with this in mind, let's proceed to give the formal definitions to all these things. If we have a set G equipped with a multiplication operation, pairwise multiplication, that takes, say, G cross G into G, so takes pairs of elements and maps them back into G, such that the G is closed under that multiplication, so for any G and H belonging to G, GH is also in G, then such a construction is called a semigroup. If additionally two further conditions hold, one, that there be a unique unit element, so there exists a unique element E inside G, such that for any G inside G, E, G is the same as G, E is the same as G. That's the first condition, that there be a unique unit element, and the second condition, that for every element in G there should be a unique inverse that is also in G. So for any G inside G, there exists a unique G minus 1, such that G minus 1 is the same as G minus 1. G is the same as the identity element. So if these conditions hold, then this is called a group. So to summarize, a multiplication operation on a set must be closed under that multiplication operation. There should be a unique unit element and there should be a unique inverse. In that case, it's called a group. Now, this multiplication operation needn't actually be commutative, but in the case where the elements do commute, so if for any G and H belonging to G, HG equals GH, then the group is called abelian group. Two-dimensional rotations, for example, are an abelian group because it doesn't matter which order you apply a rotation around a given axis, but three-dimensional rotations are clearly not, because the order of application of those rotations in three dimensions starts to matter. Now that's another definition here. The next one is that the order of the group is equal to the number of elements in it. So order is the number of elements, to use MATLAB notation, of G. It could be finite, and it could be infinite. For example, for Lie groups, as we'll see, the order is infinite. Now, if we have a subset in G, which is itself a group, that is, it's closed under this multiplication, it contains the unit operator, and it contains the inverse of every element that it contains, then it's called a subgroup. A subgroup can just be a unit element in the most simple case, or it could be the entire group, or it could be something in the middle. So things like C3V, yeah, the symmetry group of ammonia, does contain C3, just a rotation around the axis, as a subgroup. And C3 contains, for example, the identity group that simply does nothing as a subgroup of either C3 or C3. Right, so if two groups are related by a mutually unique map, so if there is a map, mutually unique map from group G to, let's say, group W and back, then the two groups are called isomorphous. And clearly they would have the same number of elements, and all the properties would be retained. In particular, isomorphism has to preserve the product. So if this is, let's say, a map M, so M maps G into W, then for any G and H belonging to G, M of GH must be the same as M of G times M of H. So any such map must preserve the properties of the group, in that if we've got a product of two elements inside G, then it should map into the product of their images inside W. Now, examples of groups are plentiful. I already mentioned finite groups. Another good example is the propagator group that we use for time translation, quantum mechanical simulations. And it's fairly easy to demonstrate that that's in fact a group. Let's just go through the conditions and show that it's the case. So a propagator is something that looks like that, minus I, H, T. And it's an operator that takes a quantum system forward by a time t under a Hamiltonian H. Okay, so there exists a product. Yeah? If we take an exponential with time t1, and an exponential with time t2, and take a product of them, then the result is another exponential, minus I, H, t1 plus t2. So clearly the set of all propagators is closed under multiplication, because when we multiply two propagators, we get another propagator. It's not the same exponential form. Okay, so closed. There clearly exists a unit propagator in there that corresponds to time equal 0. So x minus I h 0 is just the unit matrix that does nothing to the system. And if we multiply any propagator by a unit matrix from either side, we get that propagator. So that's the unit element. And for each propagator inside our propagator group, there clearly is an inverse, and the inverse of x minus I h t is just x plus I h t, which accomplishes the translation backwards in time, but it's still a unitary time translation, and so it belongs to the same group. So, see, it turns out that something that we are fairly used to has, as we'll see further on as well, fairly elegant mathematical structure. In particular, we've got it as a group. Now, importantly, if the system contains relaxation, decoherence, then it's not sometimes the case that you can take the system backwards. Let's say it has decayed to 0, or some thermal equilibrium, and lost memory completely as to what its original state was. In that case, the inverse disappears, and we are back into a semigroup, which didn't have that requirement. So the set of all propagators with Hermitian Hamiltonians or Hermitian Liouvilleans is a group. But the set of all propagators with non-Hermitian Hamiltonians, the Hamiltonians that contain relaxation, is in general a semigroup, because the inverse might not exist for every operation. So that's one example of these things. Clearly, the definition of a group is fairly restrictive, so it's reasonable to ask what is the biggest group out there. Now, because we usually work with matrix representations in quantum mechanics, the question is, what is the biggest group of n by n matrices? And if we look at this, all matrices are closed under multiplication. You multiply two matrices, you get a matrix. Unit matrix is always there, but it's not always that a matrix has an inverse. So we have to impose a requirement that the matrices that go into our set G be invertible matrices. And so a group of all n by n invertible matrices matches this, has a unit and has an inverse, and the group is called GLNF if it's over a scalar field F. If it's complex numbers, as it usually is in our case, it's GLNC, and that's the general linear group in n dimensions over the field F. That's the biggest matrix group out there, and all other groups of matrices n by n are either subgroups of GLN or are isomorphous to GLN. Now, there are three definitions that relate to the number and the density, so to speak, of the elements in the group. If we look specifically at matrices and we draw the biggest group there is for matrices, the GLN, and we look at the elements of our actual group that will be positioned somehow in there, then there can be three distinct cases. If around each element we can draw a radius that does not contain any other elements of the same group, so in other words, if we have an element G and we draw such a radius inside GLM that for all H inside GLM sufficiently closely to the point, so less than some small number epsilon, and if this radius does not contain any other elements of the same group, then the group is called discrete. But if for any value of epsilon there are still elements around a given element that do belong to the same group, the group is called continuous. Now, in the case of discrete groups, we can count them, and if there is a finite number of elements in the group, symmetry group for example, for benzene, then the group is called finite. And in the case of the countable but infinite number of elements, it's infinite. Continuous groups are obviously infinite as well. Now, for continuous groups, rigorously speaking, the definition of a continuous group, or a Lie group in other words, is that it should be a differentiable manifold as well as a group. That is, for any element G inside our group, there should be something that's called parameterization. So there should be such a set of parameters as would make the element of this group a function of those parameters. So Tn, let's say there will be n parameters, and in a small epsilon neighborhood of the element G, this should be differentiable. In that case, if such a parameterization exists at every point in the group, then the group is called a continuous group or a Lie group. Now, there's quite a few practically useful Lie groups, which I will simply enumerate for you now on the board. Now, the biggest one that we mentioned already is GLN. GLN, so all invertible n by n matrices. We could impose a restriction on it. We could request all invertible n by n matrices with a determinant equal to 1. This is often necessary when we're dealing with rotations to eliminate the inversion contribution. In that case, it will be a special linear group, SLN. So all invertible n by n matrices with determinant equal to 1. There is also a unitary group of all unitary matrices. Being unitary clearly makes the matrix invertible because the conjugate transpose is the inverse. Then inside the group of unitary matrices, which are having usually the complex elements, if we look at the analog over the real field, we'll arrive at the orthogonal matrices for which the transpose is the inverse. So all orthogonal matrices. And the special variance of either, if we also require the determinant to be equal to 1, then we get for orthogonal groups SON. So all orthogonal matrices with determinant 1, and SUN for the unitaries. So all unitary with determinant 1. In particular, these guys correspond to rotations in n-dimensional space, and these guys correspond to unitary evolution in n-dimensional space. And many of you have by now heard about SO3, which is a three-dimensional group of rotations, and SU2, which is the dynamical group of a spin half particle. Now, there's a bunch of extra definitions and things in your handout. They belong to our big spin dynamics course. In this lecture course, we'll just skip them, and we'll move to defining algebras and then to exploring the connection between groups and algebras. Now, an algebra is something that's superficially similar, except there is no requirement for there to be a unit element or an inverse. So, if we have a set A, which is a space, and we additionally define a product on it that takes A cross A into A, so pairwise matrix product in our case, and the following conditions hold, so it needs to be closed under it, so for any A and B in A, the product belongs to A. Then there should be the left distributivity for that product, so A plus B times C should be AC plus BC. There should be the right distributivity, so A plus B times C. From this side should be CA plus CB. And finally, there should be the associativity for the multiplication by a scalar. So for any A and B belonging to the algebra, and for any alpha and beta belonging to the field over which the original space was, so complex numbers in our case, so alpha A times beta B, we should be able to take the scalars out, so that should be equal to alpha beta, then A, B. And if that holds, then we have an algebra. Now, the algebra, because it's built on top of a space, it inherits the scalar product, if there was any. It inherits the basis sets, including the orthogonal and orthonormal and such like. And importantly, it inherits the various expansions and linear combinations that we looked at in the previous lecture. So, say we have an element A, and we can expand it with some coefficients, alpha and En, in the basis set En, which spans the whole of the space that the algebra is built on. And say for an element B, we can have a similar expansion, the sum over K, beta K, E, K, with the same elements of the basis set. Now, what's important is, because any element of the algebra can be expanded as a linear combination of the basis elements, the same should be true for the products of basis elements themselves. In other words, the following should be true. En times Ek should be a linear combination of the same elements. So it will be a sum over some index M, C, N, K, M, E, M. Now, the reason why this is important will become clear in a moment. Say we multiply A by B. So AB will be the product of the corresponding sums. So a sum over N K, alpha N, beta K, E N, E K. And from this, we know that we have this expansion. So that is also a sum over N K, alpha N, beta K, C, N, K, M, and we need to add a sum here over M, E, M. And so you see the coefficient that appears in front of the m's basis element here is completely determined by the expansion coefficients of A, expansion coefficients of B, and these coefficients that come from the expansion of the product. So in other words, if we look at gamma m, so the coefficients of our AB, then they are equal to a sum over n k of alpha n, beta k, c, and k m. So you see, the expansion coefficient of a product of any two elements is determined by the expansion coefficients of those elements, and also this array of numbers c and km. This is a very important array, and they are called structure constants. And the reason why they're called structure constants is precisely this, that they completely determine the behavior of the algebra under the multiplication. So, in other words, they uniquely define the algebra. Where this appears in practice is, I guess some of you have done quantum chemistry by now. You may remember that for Gaussian functions, the product of two Gaussians is another Gaussian at the center of gravity. In that case, these structure constants are very, very simple. For spherical harmonics, a product of spherical harmonics is a linear combination of spherical harmonics. A product of two Wigner functions is a linear combination of Wigner functions. So in all those cases, and well, a product of operators is a linear combination of operators, we are dealing with algebras, and those coefficients in those linear combinations are obtained from the structure constants of those algebras. What I will now do is repeat the definition I just gave for the algebra, except this product will now be a different operation. It will be a bracket called a Lie bracket, and the set needs to be closed with respect to that Lie bracket, but it also needs to have the following properties. 1. For any A, B, and C belonging to the space A, and for any alpha and beta, we could have said F, the field, without giving any particulars, but by now we've moved so close to quantum mechanics that I will actually assume complex numbers in here. Alpha and beta belonging to the field of complex numbers. The bracket needs to be what's called bilinear. That is alpha A plus beta B bracket C must be equal to alpha A C plus beta B C. And it should be bilinear from the left, and it should also be bilinear from the right. So A commutator alpha B plus beta C must be equal to alpha A B plus beta A C. The second condition, and this is where it becomes different from the ordinary product, is the bracket is antisymmetric. That is, for any A and B in A, B must be minus B, A. Third, something called the Jacobi identity has to hold. For any A, B, and C inside A, the following crocodile has to be equal to 0. A, B, C plus B, C, A plus C, A, B must be 0. And condition number 4 is where mathematicians start to differ from physicists in the way they define Lie algebras. So, in mathematics, for any A and B belonging to A, the bracket must belong to A, but in physics, for any A and B belonging to A, I times a bracket must belong to A. So, see the difference? The reason this is used in mathematics is the field, of course, needn't be that of complex numbers, and that's the only way they can define it, because not all fields have got a complex number. In the case of physics, we are not particularly interested in anything other than complex numbers, and the reason why we are doing this is in the fact that usually in quantum mechanics we work with Hermitian operators. And if A is Hermitian, and B is Hermitian, then the problem physicists have is AB, commutator, is actually anti-Hermitian. It's fairly easy to prove. AB minus BA is BA minus AB, and if all of them are Hermitian individually, that's BA minus AB, that's minus AB minus BA. This is rather inconvenient because we'd like our operators to stay in the Hermitian manifold. When we do the various manipulations with them, ideally they still need to correspond to physical observables, and so have real eigenvalues, and so be Hermitian. But the commutator with an I in front actually does stay Hermitian, and so we are using it. The other reason for this is, of course, most of our equations contain that commutator. If you remember the Liouville-van Neumann equation for the density matrix, d rho by dt was minus I h rho. And so it's quite natural that we should have the closure under this kind of bracket, because then the time propagation wouldn't take us out of our Lie algebra. So these are the reasons for the differences, and if you look at mathematicians' textbooks, they use this, and the physicists lose intuition instantly as soon as they've chosen some non-symmetric matrices for a basis set, but the physicists stubbornly use this because it corresponds to physical reality, which mathematicians needn't be bound by. Now, a Lie algebra behaves in a similar way to the algebra as regards to structure constants. Any element has an expansion, because we have inherited the scalar product, the linear combinations and such like from the underlying space. So a sum over n, alpha n, e, n. And we no longer have a plane product, but we have a Lie bracket. And so I, E, N, E, K, the commutator, because it's also an element of our Lie algebra, it has to have a similar expansion. And so it will be C, N, K, M, E, M, sum over M. And you might start recognizing familiar things in here. Remember those commutators for the angular momentum. Lx, Ly was I, L, Z. And remember I told you that these commutators are hugely important. They're more important than the normalization. And the reason why they are important is that they are in fact the structure relations for the corresponding Lie algebra. And the structure coefficients determine the algebra fully. And so it is rather important to keep these coefficients here, because it is they that determine how our Lie algebra actually behaves. What's now left for us to do is to connect the Lie algebras with the Lie groups. And in order to do that, I will analyze the properties of matrix exponentials. Some of that we already saw for the time propagators, but let's just do it in the more general case. So the following properties are either obvious immediately or can be proven without too much effort. The first thing is that the set of matrix exponentials is actually closed under multiplication. That is, for any A and B belonging to the set of n by n matrices, which is incidentally called GLn, the small g and l, the biggest Lie algebra there is of just all matrices out there. There exists such a C, and it's unique, that e to the C is e to the A, e to the B. And for the proof, you can look up that Campbell-Baker-Hausdorff formula. C is a complicated commutative series in A and B. Second, for any A in G, N, in the set of all n by n matrices, e to the A inverse is just e to the minus A. Yeah, because if we multiply e to the A by e to the minus A, the indices just cancel, we get e to the 0, which is equal to the identity matrix. So from this already, we conclude that matrix exponentials are a group. But what we can also now say is we can take advantage of this expansion. So instead of just having e to the A, which was a group, but we could say nothing about it being a continuous group because we required parameterization, what we now have is exp of the sum over n, alpha n, A, or E it was, the basis set E m. And you see now we have a parameterization. We have those parameters that parameterize the group in the vicinity of any specific element, and clearly this is a function that is continuous and differentiable with respect to alpha m. And so it turns out that if we have a Lie algebra, there is a map accomplished by this exponentiation into a Lie group. And what now is left for us to do is to match up the groups that we already have seen with their corresponding algebras. And to do that, I need to add a few more properties to this, which aren't related to the definition, but will make the job a little bit more convenient. Let's put it number 3, that a determinant of e to the A is equal to e of the trace of A. In other words, if a matrix is traceless, then its determinant is equal to 1. And 4, if A is Hermitian, then exp IA is unitary. Okay, let us now remember the list of the groups that we had and try guessing the corresponding algebras. We had G, L, N, we had UN, we had SUN, we had ON, we had SON. Right. So GLN is the biggest group of all invertible matrices. The only thing that we require is the property that's already there for every matrix exponential, and so the corresponding algebra would then be GLN. The algebra of all n by n matrices, because no matter which matrix we put into here, its exponential is going to be invertible and therefore belong to GLN. And so the exponential map takes the algebra GLN into the corresponding group. Here, for UN, in order to have a unitary exponential, we need to have a Lie algebra of Hermitian matrices, and not forget the fact that we require the I in that commutator and also the I in the exponential map. So it's quite important that we've got I in here in all cases. So under exp IA, the unitary group is obtained by exponentiating Hermitian matrices in such a way, and the corresponding algebra, expectedly, just to match the notation, got the name UN. Now, here, S was about the determinants. We had to have our determinants equal to 1 in SUN, and so the corresponding algebra must, according to this, have Hermitian operators in it, and according to this, must have traceless. So SUN is a Lie algebra of all traceless Hermitian operators. And as you know, spin operators are traceless and Hermitian, and so in our case, SU2S plus 1 is in fact a dynamical algebra of a spin S. And for the rest of them, the procedure essentially repeats. So this is called OM, this is called SOM, and they are composed of such matrices as produce the matrices from this group upon exponentiation. There's a huge table in your handout that gives the exact relationship between the groups and their corresponding algebras. Right, the last thing about Lie algebras that we need to consider is the concept of the adjoint representation and the adjoint action. Imagine a particular algebra with some elements in it. What we can define is the action of an algebra on itself by commutation. So let's pick a particular element in here and call it A, and then let's define a map by a commutator with A from an algebra A into itself. That is, we take an element of an algebra and we commute it with A. In the context of spin dynamics, you may remember we had something similar. It was called commutation superoperator. It was acting on our density matrices and giving us some other density matrix. This is exactly that. And the action is called adjoint action, and the corresponding operator in quantum mechanics is usually denoted by a double hat. So that would be H double hat acting on rho. In mathematics, the notation is add A, acting on B, is a commutator of A and B, where I just kept the operator hats to make it similar to quantum mechanics. Now, there are various relations one can prove about it. They are given in your handout, but in particular, what we call a transformation between Hilbert space and Liouville space in spin dynamics, mathematicians call the adjoint map. And what we call superoperators are the adjoint action by the operator on a particular algebra, so it is an action by commutation. The last topic for today is representations. As you know, not all operators are matrices. Some of them are, for example, derivatives. Rotation, after all, is a physical process. And the procedure of obtaining matrices which have the same properties as the operators under multiplication and other things is called the process of obtaining a matrix representation. In other words, if we have a group G, we require a map from that group into GLN, GLN-R or GLN-C, depending on what the context is. So a representation is a map from our group, which could be a group of some physical transformations, into a group of matrices, GLN over a suitable field of scalars. Now, representations can have different levels of faithfulness, as it were. If no information is lost in this map, then the representation is called faithful. A good example would be quantum mechanical operators. If we pick up an orthonormal set of functions, then a representation P of an element G, I, K would be just the thing that we are used to in quantum mechanics, phi I, G, phi K. And if phi is a complete basis of our wave function space, then the matrix representation is just as good as the operator representation. This is the equivalence between the Schrödinger and the Heisenberg formulation of quantum mechanics. One was done in terms of functions and operators, the other was done purely in terms of matrices. On the other extreme, we could have gone and mapped every single element of the original group into a number. For example, number 1. So if P maps any element of the group into just 1, then the properties of a group are nominally satisfied in the resulting representation. Clearly there's a unit operator in here, clearly there's multiplication, you can multiply 1 by 1 and get a 1, so it's closed under it, and 1 is its own inverse. So this is a very simple group, but clearly a lot of information is lost in such a transformation, and representation of this kind is called lossy. And in particular, this specific one where everything is mapped into just one number is called a trivial representation. But in general, of course, we would have matrices. Now, once we do have those matrices, a question is whether a given matrix representation can be in any way simplified. It turns out that sometimes a question has an answer, and there are two categories of representations. There are reducible ones and the fully reducible ones. Two fully reducible. Now, a reducible representation is the one that can, by some similarity transformation, be taken into the following form. P1 of G, some matrix X of G, and P2 of G, and this is 0. So these are matrix blocks, and this should be achieved simultaneously for all G in our group. If that's possible, then the representation is called reducible. If we can also get rid of X, and so we can make it into P1G, P2G, and maybe other diagonal blocks, and the rest are zeros, then the representation is called fully reducible, and as soon as we've achieved a situation where it cannot be reduced any further, these individual blocks become called irreducible representations, because they themselves cannot be reduced or blocked out any further. And the catch, of course, is it has to be accomplished simultaneously for all elements of G, and so this is not always possible. Now, if the set of matrices obeys a certain set of properties, then if they are blocked, their blocks would individually obey the same properties. So in a way, these blocks would be representations of the same group because they retain the same properties. They might be lossy, they might be lossless, but they are called irreducible representations. And this is something that you hear fairly often, particularly in the context of molecular orbital theory in chemistry, where these things can save a significant amount of computing power, because once you've block diagonalized your matrices, you can treat individual blocks separately. There is a theorem for irreducible representations, which is hugely general and very important, but which I would not prove because it takes a very considerable amount of time, and we really don't have that time in our course. It's called the Great Orthogonality Theorem, and it makes it, well, I guess it encodes the fact that these individual representations are orthogonal as matrices. Here's the formulation: root NA NB over NG. These are the dimensions of the representation A and representation B. G and G is the order of the group. A sum over the elements of the group. This is a fairly unusual sum that some of you may not have encountered before. We are summing over the group of matrices PA of G complex conjugate JK, PB of G LM. So this is a matrix of element G in a representation, irreducible representation A, its JKth element. This is a matrix of G in irreducible representation B, its LM's element. And once you've taken the sum over all the group elements, what you get is delta AB, delta JL, delta KM. So 3 sets of orthogonality conditions on those irreducible representations. The equation as it stands might appear quite arcane, and its usefulness might not be immediately clear, but we will take advantage of it at least once in this lecture, but it's of very general usefulness in the representation theory at large, and is certainly used extensively in simplifying the various calculations, particularly of the kinds that occur in quantum chemistry, where having a symmetry can make a difference between a problem not being computable and just about computable in big enough cluster or some such thing. Right. The last thing about representations of the groups, and of course once we've got a representation for the group, we also have a representation for the algebra, because this is what it gets to under the exponential map. A character of a representation of a rep is a trace of the corresponding matrix. And chemists certainly came across characters in molecular orbital theory. Physicists presumably did in particle physics, but characters allow those block diagonalization operations to proceed in the actual chemistry calculation context. An important property of characters that's proven in your handout using the great orthogonality theorem is they are also orthogonal as vectors. So a sum over all the group elements in the group of a character of a representation A of a group element G, complex conjugate, times a character of an irreducible representation B of an element G is delta AB. So the character strings are orthogonal as vectors between different representations. Where they're useful in chemistry is in the generation of the so-called symmetry-adapted linear combinations. Those are linear combinations of basis functions that remain invariant under symmetry transformations. So if we have, say, ammonia and H, and we are looking at the various symmetries of this molecule, it's clear that the sum of 1s functions on all 3 hydrogens would remain invariant under those transformations. That's an example of a symmetry-adapted linear combination. The reason they are important is they block diagonalize the symmetry operations, and because the Hamiltonian commutes with the symmetry operations, they also block diagonalize the Hamiltonian. And as soon as the Hamiltonian is block diagonal, individual blocks can be treated and calculated separately, and it can make a huge difference in the amount of computational time required. I've given you the expressions for the symmetry-adapted linear combinations and a few examples in the handout, but really, because this course is, at least this lecture is about definitions and not applications, applications will be a whole separate lecture series. We should leave it there. One last thing that I'll mention is a difference between the symmetry treatment in Hilbert space and the symmetry treatment in Liouville space, which, as we figured out a moment ago, was the adjoint representation of the operator algebra. If we take a look at wave functions, for example, a singlet, alpha, beta, minus, beta, alpha, over root 2. Because of this minus, it is anti-symmetric with respect to label permutation. Yeah, you swap the 2 particles around, a minus pops out in front. However, if we project this into the Liouville space and we look at the corresponding density matrix, it will be the following. It's alpha, beta, minus, beta, alpha, then another one, alpha, beta, minus, alpha divided by 2. So that's the corresponding projector. Now, if we now swap the particles here, a minus would pop out in front of this, another minus would pop out in front of this, and the whole thing will remain as it was. So the bottom line is anti-symmetric irreducible representations in Hilbert space are all mapped into the fully symmetric irreducible representation in individual space. What that means in practice is that as soon as your Hamiltonian is blocked out in individual space, it's really only just one block that needs to be simulated because everything else is irrelevant. Even in Hilbert space, if the system has started in just one of the blocks, because they're not connected, it will just stay in that block, and so the calculation can only be carried for that block. In practice, it can mean a reduction in computation time, sometimes by several orders of magnitude, because irrelevant calculations are not carried out here. And once they get started in a particular block, quite a few processes, including relaxation, because they obey the system symmetry, will just keep it there. So because relaxation is the ensemble averaged Hamiltonian squared, it will retain the symmetry that the Hamiltonian had and also get block diagonalized under these transformations. Right, that's it for today really. As a considerable amount of information, you have a huge handout of 13 pages. Skip the things that I've skipped on the board. The handout contains a considerably greater amount of information that will actually be asking for you to memorize and understand. But it's a surprisingly fruitful area in that once you get the connection between the physical properties of your spin system and the algebraic properties of the associated mathematical formalism, the understanding gets considerably deeper. And in many cases, a huge amount of calculations, certainly on computers, can be saved if these properties are taken into account.